Hi everyone, and welcome to this Godot tutorial on how to make a simple finite state machine. By the end of this video, you'll know the basics of this tool, and you'll know how to implement one in Godot 4 and C# using a hierarchy of nodes. However, we're not actually going to make a character today. Rather, we're going to focus on a simpler and less studied example. But that's just as important because it demonstrates how state machines can also be useful to environmental props. Because we're going to create a basic traffic light. I know it might not sound like much, but trust me, it will teach us a lot. And it's actually just one proof of the fact that your game environments should live and breathe too, even though they contain inanimate objects. Of course, if you want to get this basic traffic light 3D model I made, or the code for this tutorial, don't forget to check out the GitHub repo with all my Godot tutorials over here. And as usual, since we'll be coding or logic in C#, make sure that you have a version of Godot with the .NET support enabled. Okay, and now, with all that said, let's discover how to set up our first finite state machine in Godot and C#. Now, before we dive into the implementation per se, let's briefly recap what a state machine is. Note that I won't do a full in-depth explanation here, because I've actually already discussed this topic several times on my channel, and although my past tutorials were using Unity, the core underlying concepts remain the same. So you can absolutely go and check those out for some extra details. In short, a state machine is a programming design pattern where you chop down an entity's behavior into several states that each have their own context and logic, and are part of a big machine that can transition between all of those states on specific events. A finite state machine, or FSM, is a state machine with a finite number of states, which is usually the case in gamedev since modeling continuous and infinitely defined phenomena is really an edge case. What's nice with this model is that it's quite intuitive, and in particular it's great for character AIs or objects that you can interact with. So all of that is why it's widely used in the video game industry. It's been there for a long time, and it's still here today. In an FSM, you always have only one active state at any given point, which we often call the current state, and you also have an initial state, which is the state that will be active when the machine first starts. The transitions then take the machine from one state to the other. Note that you might have just a few states or a bunch of them, that you may not have transitions in every direction between all of your states, and that these transitions can be triggered by a variety of events. For example, they can be linked to physics checks, or just occur after a specific amount of time, or be explicitly called when the player does some action. Then, inside each state, you have some logic that is specific to this state, and is therefore only executed when the entity is in this state. So in a basic FSM, you don't have overlap between your states. Remember that you can be in two states at the same time. Now, usually the logic of a state is chopped down into the common lifecycle hooks of a script. So you can have the ready function, the process function, the input event hooks, and all that sort of stuff, because you basically want to match a normal behavior lifecycle and have the state machine proxy these calls to the current active state. But we also give states two additional functions called the enter and exit functions that are used to initialize or clean up context-specific data for the state when we transition to or from it. Of course, depending on your state machine, two states can be quite similar or really different. But usually, it's important to try and avoid code redundancy. And it's also always interesting to try and keep your states as decoupled as possible. Because as soon as you start to add some coupling and dependencies, you basically run the risk of having something missing or updating some part of your codebase and then the rest doesn't work. So yeah, in all generality, the more decoupled your states, the better. Now, of course, because of the structure of an FSM, there's almost always some minimal level of coupling between your states, because in particular, in most implementations and in the one that we'll see today, states need to know about the other states available so that they can transition to them, at least have a reference of some kind. In Godot, as explained in the official docs, there are three common ways of creating an FSM. Either you have one node per state in your entity's hierarchy, and you enable and disable those according to the current state of your machine, or you have a big manager script that switches between the code branches to run using some kind of enumeration, or you dynamically toggle state scripts depending on the active state at runtime. Here we're gonna go for the first method, so we'll basically have one node per state, in our case the 3 green, orange and red states of the traffic light, and we'll swap them out as our state machine updates. Alright, now that we know what we want to do, time to jump into Godot and create our basic FSM. Okay, so as we said, our FSM will rely on nodes to define and toggle states. Since these states don't have really a direct meaning in a Godot hierarchy, they're just holding a branch of our state machine, we'll use the simple node type for those node states. And then if we need specific features, we'll add more specialized nodes as children. We can then group all of those nodes under another basic node for the state machine itself, or in other words, the top manager that lists all the available states and calls the right methods of the current state to execute its logic while the machine is running. Now we need to create our C# scripts to actually give life to our FSM. Let's start with the state machine itself. As we saw in a previous tutorial, we can do so directly by right-clicking on a node and clicking the Attach Script option. We can leave the default options and click the Create button to actually create our script resource. For the states themselves, it's a bit more tricky, because we're going to use an intermediate abstract class called state to implement the base structure and possibly default logic that is common to all our states. Basically, by having this base class and then creating subclasses that inherit from it for each specific actual state, we'll ensure that we have a shared model and C# type, and we'll enforce our actual states have all the necessary elements to function properly. So again, just to be clear, this state C# class will not be instantiated directly. We won't use it as is. We'll only use derived classes that use it as a parent class. Okay, so this time, let's create our base state script as a standalone resource in the project, by right-clicking the file system doc, because again, it's not linked to any particular node. Then we'll double-click on it to open it in Godot's built-in code editor. This class will be quite simple, because it's just meant to define the structure of a state. So we'll basically fill it with some virtual functions for the important moments of our object's lifecycle, so the enter and exit of this state, its initialization with the ready function, its update, be it the basic process routine or the physics one with a fixed time delta, and the input events handler. And also, let's add a public reference to our parent state machine instance so that any state can trigger a transition to another state by calling a public method on this object. However, if you're a bit used to C#, we won't actually make it abstract, because we have to leave it as a node so that further down the road, our derived class can actually be put on Godot nodes in the hierarchy. Okay, so anyway, of course we might not need all of this in our example, but at least it makes for a generic C# class that could be reused in another project to create more advanced states in the future. By the way, the reason I'm using virtual functions here is because I want them to be optional, so I need to give them some default empty code to ensure that it falls back to this null implementation if we don't override it. But at the same time, making them virtual will allow us to indeed override some of them, because it's essential since it's how we'll create our actual per-state logic. Okay, now that our base state class is ready and our codebase knows about this abstract type, we can go and take care of our state machine manager script. To put it simply, this class will need to do 4 things. 1. Get a list of all available state nodes and keep references to their state scripts. 2. Keep track of the current state, the one to run the logic for. 3. Actually run this logic for the current state by calling its various hooks and basically delegating the Godot built-in hooks. And 4. Handling transitions between states. Let's start by defining the initial node as a node path and giving it the export attribute. This will make sure that we have a little slot in our state machine nodes inspector where we can drag another node from our hierarchy, to mark it as the initial state for FSM. But if you actually take a look at the inspector, you see that for now nothing's appeared in the node's inspector. That's because, contrary to GDScript, C# needs to be compiled before changes take effect. This is done automatically when we play our game, but not by default in the editor. Still, we can of course do it easily by going at the bottom to the MS Build tab and clicking the Build button in the Settle dropdown. Once it's done, you see that our new input is available in the inspector. So let's assign it by picking our green node. Now let's go back to our script and add a dictionary for a list of states, and a state variable for current state. Note that the dictionary is a basic C# type that allows you to match a key to a value and requires the system.collections.generic library import. Okay, so the dictionary of states will use the name of the node as key, so this will be our state reference, and the state-derived class instance as value. In the ready function, we'll initialize our machine by doing a couple of things. First off, we'll go through our child nodes and fill in our dictionary. We'll also take this opportunity to assign the reference to the state machine instance inside each state to our current script object, run the ready function to initialize them, and run the exit method to be sure that they are properly reset. And finally, we'll set our current state to the initial state by converting our node path and, of course, enter our current state. The next step is to delegate all of the built-in hooks of Godot to our current state. So we'll do this for the process function, the physics process function, and the events handler called unhandled input. Again, we might not use all of this here, but we want to make something generic, and so this state machine should cover most cases, even in more advanced projects. And last but not least, we just need to add our transition function, which will take in the name of the state to transition to, so it's key in the dictionary, check that it's actually in the list, and that we're not already in this state, and then if all those checks pass, get it by its key in the dictionary, exit the current state, update our active state reference to the new one, and finally enter this new state. Okay, so at that point, we have all the architecture we need to actually create states based on our abstract state C# class and integrate them in our FSM to give life to our traffic light. Okay, so now that our overall structure is ready, let's see how to create an actual state logic. We'll start with our initial state, the green light. We can create our green state class by right-clicking in the file system doc with the default options, but then of course we need to remember to have it inherit from our state class, and we can remove the ready and process functions. The logic of this state will be really simple. When we enter this state, we'll turn an actual green light 3D object in our scene on and start a little timer. Then, upon completion of this timer, we'll turn the light back off and transition to the orange light state. So let's come back to our scene and prepare those additional elements. Inside the green node, as children, we'll add an OmniLight 3D, which is Godot's 3D point light node, and also a timer node. For the light, we can just change the color and lower the energy a bit. For the timer, let's make it run for 2 seconds before timing out, and also make it a one-shot, because once we transition to another state, we don't want this timer to keep on running at the same time. Now in our green state code, we can use getNode to get those child nodes in our enter state and initialize our context properly. The light simply needs to be shown by setting its visible property to true, and for the timer we have a self-explanatory start function that we can call. But now the question is, how exactly are we gonna know when this timer is finished? Well, in Godot, there's this really great concept of signals, which are sort of Godot's version of events. Basically, almost any node in Godot has signals that it can send at specific times. And you can super easily connect to them with your own callback functions to react to those events in your code. To see the signals available on a node, we just have to go on the right, where we have the inspector, and switch to the Node tab. This shows us node-specific data, and in particular, all the signals available for current one. And you see that for this timer node, we have a timeout signal at the very top, which is the signal that will be triggered when the timer is finished. To connect to it, we'll simply double-click on it, and then we need to pick the node in the hierarchy with the script that should contain the callback function. I'll change the name of the function to match more the usual C# casing, and then click on Connect. You see that it just added a function at the end of our green state script. Now, be careful, cause with C#, Godot's not yet completely perfect in terms of boilerplate, so we actually have to move this function back inside our class. But then inside the function, we just need to call the transition to the orange state. And then we can make our override of the exit function, where we turn a light back off, stop our timer just in case we exited our state because of something else, and so our timer is not actually finished, and we're done. Our green light state is now ready. Now, of course, we're now stumbling upon one of the drawbacks of state machines, which is that you can't really test them until all, or at least most of your states are ready, since they depend on each other. But luckily for us, in this basic example, the other states are extremely similar, so we can just duplicate our script a couple of times, rename the file and the classes to orange state and red state, and then update the transition target states. Also, of course, don't forget to add light and timer nodes to the orange and red nodes as children with the same kind of options as before. Again, if you want to check out the exact way that I set up my scene, don't hesitate to have a look at the GitHub and you'll find all the files for this demo. But now guess what? We can actually run our game and test our basic state machine. I've prepared a little demo scene with a bit of environment properties to make it easier to see our traffic light, so I'll just drag my traffic light scene into it, and here we are. You see that we now have a very basic traffic light that cycles through green, orange and red. Okay, that's great, but as we said before, our states are currently very similar. Actually, they're even a bit too similar. There isn't any fun in doing a state machine for this simple a behavior. So to wrap up this tutorial, let's add some specificities for a few states and see how easy it is to boost our entity's behavior using a state machine. A first easy change that we can make is inside our node hierarchy, play around with the timer node properties to change the duration of each color. That's an example of how our FSM system can easily be tweaked in the inspector, no code required. So that's an advantage of using nodes to define your FSM states. But of course, we can also do more advanced stuff by diving back into our code and extending our state classes. For example, let's say that we'd like our orange state light to be a bit old and start to flicker anytime we light it. Well, we can do this easily thanks to a noise map and our update function. As explained in this quick tutorial by Forest, we can create a noise generator instance and then use it to modulate the alpha or the energy of our light. Note that in Godot 4, the built-in random number generator is now the fast noise light. So we're going to make an instance of this class, set it up in our overridden ready function, and finally get a reference to our light component so that we can change its energy in the overridden update method. Here I've simply passed it back Forest's formula. And that's it. If we run our game again, you see that as soon as the traffic light goes to orange, it starts to flicker. And what's really great is that we didn't have to change anything else but our orange state class. So we basically have improved our behavior, and we could add a lot more without having to change anything in our codebase architecture, and without cluttering the rest of the code with those new context-specific variables. Another cool thing would be to be able to manually force a state, instead of waiting for a timer. For example, what if we had a big red button that we can press to stop the traffic instantly by having our traffic semaphore jump to the red light? Now, I'm not gonna go in details on how to set up the button, or the events and signals that it emits and that we can react to. cause this tutorial is already quite long, and some of the shortcuts that Godot provides in GDScript aren't totally transferable to C#, so it requires a bit more work. But let's just assume that we have this big red button, which, when we left-click on it with our mouse, emits a global basic C# event in our game called redButtonClicked, in a static events class. Then, all we have to do in our red state script is, in the ready function, register a callback for this event, and then define this callback below to force the transition to our own state, so the red state. Note that these parameters are required for this kind of C# event, even though we're not actually using them. And also a quick note, don't forget that we run the ready function of all of our available states when the machine is first set up. So even if we've never entered this state before, this code will still be executed when the game first starts, and so our callback will be available at all times. But with all that said, we're actually done implementing our first basic finite state machine in Godot. If we try this out, you see that we can now click our button to instantly jump to or stop red light without having to go through all the cycle. But then, since we used a normal transition, the rest of the logic kicks in and our state machine eventually transitions back to green, then orange, then red, then green, and orange, and red, and etc. And on that note, that's it for today. You now know the basics of implementing FSMs in Godot and C# using Node and C# inheritance. I hope you liked this tutorial and that it helped you learn the fundamentals of this tool on a more original example. So if you did, feel free to like the video and subscribe to the channel to not miss the next ones. And of course, don't hesitate to drop a comment with ideas of Godot tricks that you'd like to learn. As always, thanks a lot for watching and take care.